Hello and welcome to Math Zone African Motives. In this tutorial, we will be tackling a question on kinematics from Engineering Science N4. Our objective for this video is to teach you how to apply vector addition to calculate resultant velocities and solve projectile motion problems. By the end of this tutorial, you will be able to calculate resultant velocity, find the maximum height and horizontal displacement of a projectile, and solve problems involving relative velocity. Let's begin with our first problem. Question 1.1 states, a ship that can cruise at 48 km in still waters sets course due southwest. It is driven off course by a current flowing west 26 degrees north at a velocity of 8 km. We need to calculate the resultant velocity in both magnitude and direction. This is a vector problem, as velocity has both magnitude and direction. We'll use the method of resolving vectors into their horizontal and vertical components. This involves two key steps. First, we resolve each vector into its horizontal, or x, and vertical, or y, components. Second, we find the sums of these components to get the resultant. Let's first visualize the problem with a diagram. We can draw a set of compass directions to help. The ship's velocity is 48 km per hour southwest. This direction lies exactly between south and west, making a 45-degree angle with the south axis and the west axis. Next, we add the current's velocity. The current flows at 8 km per hour, west 26 degrees north. This means the direction is from west towards north at an angle of 26 degrees from the west axis. Now that we have our vectors, let's resolve them into their components. The formula we use for a component is the magnitude of the vector times the cosine of the angle for the horizontal, and magnitude times sine of the angle for the vertical. We must be careful with our angles. Let's start with the ship. The ship's velocity, vitesse, is 48 km/h. To use a standard angle measured from the positive x-axis, we take 180 degrees for west, plus 45 degrees for southwest, which gives us 225 degrees. Now for the components. The horizontal component is 48 times the cosine of 225 degrees, which is negative 33.941 kW. The negative sign confirms it points to the west. The vertical component is 48 times the sine of 225 degrees, which is also negative 33.941 km/h, confirming it points to the south. Next, the current. Its velocity, Vc, is 8 km/h. Its direction is west 26 degrees north. The standard angle is 180 degrees minus 26 degrees, which is 154 degrees. The horizontal component of the current is 8 times the cosine of 154 degrees, which is negative 7.209 kW. This points west. The vertical component is 8 times the sine of 154 degrees, which is positive 3.4888 km, pointing north. We're doing great. We have all our components. Now we need to sum them up to find the resultant vectors components. The total horizontal component, which we call the sum of horizontal components, or sigma hc, is the sum of the horizontal components of the ship and the current. That's negative 33.941 plus negative 7.209, which gives a total of negative 41.150 km. This is the magnitude of the horizontal component directed west. Similarly, the total vertical component, the sum of vertical components, or sigma Vc, is the sum of the vertical components. That's negative 33.941 plus 3.488, which equals negative 30.453 km/h. This is the magnitude of the vertical component directed south. Now we have our two perpendicular components for the resultant vector. We can find its magnitude using the Pythagorean theorem. The formula for the resultant magnitude, r, is the square root of the sum of the squares of the horizontal and vertical components. This formula comes directly from the Pythagorean theorem. Plugging in our numbers, we get the square root of negative 41.150 squared plus negative 30.453 squared. Calculating this gives us a magnitude of 51.196 km/h. Finally, we find the direction. We use trigonometry. The angle theta is the inverse tangent of the absolute value of the vertical component divided by the horizontal component. It's important to use the absolute values here. So theta is the inverse tangent of the absolute value of negative 3453 divided by negative 41.150. This gives us 36.5 at 65 degrees. Now we need to specify the direction relative to the compass points. Our horizontal component was west, and our vertical component was south. This means the resultant vector is in the southwest quadrant. The direction can be stated as 36.565 degrees south of west. Alternatively, we could state it as west 36.565 degrees south. Both are correct. Therefore, the final resultant velocity of the ship is 51.196 kilometers per hour, west 36.65 degrees south. Let's compare this to the provided memo. The memo gives 51.167 km/h and an angle of 36.498 degrees. Our slight difference is due to rounding during the intermediate steps. Both our approach and the memos are valid. I've used standard component resolution, which is a robust method. The question asks for an alternative method, so let's quickly demonstrate the law of cosines and sines. Here we draw the two vectors head to tail to form a triangle. We want to find the third side of this triangle, r. To use the law of cosines, we need the angle between the two vectors. From our previous diagram, we can see the angle is 180 degrees minus 45 degrees minus 26 degrees, which equals 109 degrees. This is the angle C in our triangle. The law of cosines states that the square of one side of a triangle equals the sum of the squares of the other two sides minus 2 times their product times the cosine of the angle between them. Plugging in our values gives us 51.196 km/h for the magnitude, which matches our component method. To find the direction, we can use the law of sines. It relates the length of a side to the sine of the opposite angle. Here, angle A is the angle inside the triangle adjacent to the ship's velocity vector. Solving for sin A, we get A is the inverse sine of 0.1245, which is 7.159 degrees. This angle is measured from the ship's original path. The actual angle we want, the angle with the west axis, is the ship's angle, 45 degrees, plus this calculated angle A, all 8.487 degrees, which gives us 53.487 degrees south of west. You can see this angle differs from the memo's value. The law of sines can sometimes lead to ambiguity. In the memo's calculation, they used an interior angle of the triangle of 45 degrees, which is incorrect. The law of cosines is generally more reliable for finding the side opposite the known angle. Now let's move on to the second part of question 1.1. We need to find the distance the ship will cruise in 5 hours. This is a straightforward application of a fundamental kinematics equation. We use the formula, distance equals speed times time. We already calculated the ship's actual speed, which is its resultant velocity magnitude, and the question gives us the time. Plugging in our values, the distance s is 51.16 km/h times 5 hours. This gives us 255.980 kilometers. So in 5 hours, the ship will cruise a distance of 255.980 kilometers. Let's compare this to the memo. Their answer of 255.835 kilometers is slightly different, again due to their slightly different resultant velocity value. Our calculation is consistent with the velocity we found. We now move to question 1.2, which deals with projectile motion. The problem states, a bullet is fired at an angle of 30 degrees to the horizontal at a velocity of 400 meters per second. We need to calculate the maximum height reached and the horizontal displacement. Projectile motion describes the path of an object thrown into the air, subject only to gravity. We analyze the horizontal and vertical motions independently. Let's list our initial conditions. The initial velocity, which we'll call u, is 400 mph. The angle of projection, theta, is 30 degrees. The acceleration due to gravity, g, is 9.8 meters squared and acts downwards. First, we must resolve the initial velocity into its horizontal and vertical components. This is a crucial first step for any projectile motion problem. The initial horizontal velocity, u(x), is 400 times the cosine of 30 degrees, which is 346.410 ⁻². The initial vertical velocity, upy, is 400 times the sine of 30 degrees, which is 100 meters. Let's calculate the maximum height reached by the bullet. This is part 1.21. The question asks for the maximum height. A key concept here is that at its maximum height, the bullet momentarily stops moving upwards. This means its vertical velocity at that point is 0. So at maximum height, the final vertical velocity, Vy, is 0. We can use a standard kinematics equation that relates initial and final velocities, acceleration, and displacement. That equation is v squared equals u squared plus 2 times acceleration times displacement. Since we're analyzing the vertical motion, we'll use the vertical components. The equation becomes the square of the final vertical velocity equals the square of the initial vertical velocity minus 2 times g times the vertical displacement, Sy. We use a minus sign for g because gravity acts downwards, opposite to our initial upward motion. Plugging in our values, 0 squared equals 200 squared minus 2 times 9.8 times the vertical displacement, Sy. Rearranging the equation to solve for Sy, we get 40,000 divided by 19.6, which is 2040.816 meters. This is the maximum height. Converting this to kilometers gives us 2.041 kilometers. The maximum height reached by the bullet is 20,040 on 816 meters. The memo uses a shortcut formula for maximum height. U squared sine squared theta over 2g. If we use this, we get the same answer of 2040.816 meters. Now for the final part of question 1-2. We need to find the horizontal displacement when the bullet hits the ground. To find the horizontal displacement, we need two things: the horizontal velocity and the total time the bullet spends in the air. The relevant equation is horizontal distance equals horizontal velocity times time. The horizontal velocity, ux, we already know, 346.4 tensias axioms. It remains constant because there is no acceleration in the horizontal direction. So our task is to find the total time of flight, to total. We can find the time using the vertical motion. There are two common ways to do this. One way is to calculate the time to reach maximum height and double it. The other is to calculate the total time of flight directly. Let's use the first method. The time to reach maximum height, Tmax, is given by the formula Uy divided by g. So Tmax is 200 meters per second divided by 9.8, which is 24.08 seconds. The total time of flight is twice this, so to total is 2 times 24.08, which is 40.816 seconds. Now we can calculate the horizontal displacement. Sx equals 346.410 meters per second times 40.819 seconds. This gives us 14143.918 meters. In kilometers, that's 14.144 kilometers. The horizontal displacement, also known as the range, is 14.144 kilometers. The memo uses a different shortcut for the range. U squared sine of 2 theta over g. If we use that, we get 14139.190 meters. The difference is minor and is due to rounding in our intermediate time calculation. Both results are essentially correct. We've reached the final question of the problem set, question 1.3, which deals with relative velocity. The problem states, two vehicles start moving simultaneously at a fork in a road. Vehicle B travels at a speed of 120 km/h northeast. Vehicle M travels at 125 km/h directly east. We need to calculate the velocity of vehicle M relative to the velocity of vehicle B, in both magnitude and direction. The key phrase here is velocity of M relative to B. This means we are observing the motion of M from the perspective of an observer in vehicle B. This is a vector subtraction problem. The formula for relative velocity of M with respect to B, written as VMB, is the velocity of m minus the velocity of B of B. Before we can subtract, we must first express both vectors in component form. For vehicle M, the velocity is 125 km/h due east. The standard angle is 0 degrees. So the components are 125 and 0. For vehicle B, the velocity is 120 km/h northeast. The standard angle is 45 degrees. The horizontal component is 120 times cosine 45, and the vertical component is 120 times sine 45. Both are 84.853 km. Now that we have the components, we can perform the subtraction. The relative velocity is Vm minus Vb. We subtract the corresponding components. The horizontal component of the relative velocity is the horizontal component of m minus the horizontal component of b. So, Vmbx is 125 minus 84,853, which is 40.47 km/h. This component is positive, so it's directed east. The vertical component of the relative velocity is the vertical component of m minus the vertical component of b. V nembi is 0 minus 84.853, which is negative 84.853 km/h. This component is negative, so it's directed south. We now have the two components of the relative velocity vector. Just like before, we can find the magnitude using the Pythagorean theorem. The magnitude of the relative velocity, r, is the square root of 40.1147 squared plus negative 84.853 squared. This gives us 93.871 km/s. For the direction, we use the inverse tangent of the ratio of the vertical to horizontal components. Theta is the inverse tangent of the absolute value of negative 84.853 divided by 40.47, which is 64.685 degrees. The horizontal component was east, and the vertical component was south. Therefore, the relative velocity is in the southeast quadrant. The direction is 6.685 degrees south of east. So the final answer is that the velocity of vehicle M relative to vehicle B is 93.871 kilometers per hour, 64.685 degrees south of east. Let's check the memo. The memo's answer is 90.871 km/h and an angle of 25.32 degrees. This is a significant discrepancy. Let's re-verify our calculation using the alternative method shown in the memo. The memo presents an alternative method for relative velocity, which involves reversing the velocity vector of vehicle B and adding it to the velocity vector of vehicle M. The memo shows taking vehicle M's velocity vector, pointing east, and the negative of vehicle B's velocity vector, pointing southwest, and using them to form a triangle. This corresponds to the vector equation r equals Vm plus h of b. We can solve this triangle using the law of cosines. First, we find the angle between the two vectors. From the diagram, the angle is 45 degrees, which is the angle of VB. So the angle is 180 minus 45, which is 135 degrees. Wait, the diagram shows the angle is 45 degrees. Let's be very careful here. The memo's calculation uses the angle 45 degrees for the law of cosines. If we assume the angle B in their formula is 45 degrees, which is the angle the reversed vector VB makes with the x-axis, let's see where that leads. If we use their formula with the angle 45 degrees, the magnitude comes out to 88.81 km/h. This is also different from the memo's value of 90.871 km/h. It seems the memo has made a mistake in its calculation as well. The correct angle between the vectors Vm and Vb is 45 degrees. Let's recalculate the direction using the law of sines and this corrected magnitude. Using the law of sines and solving for the angle phi adjacent to the 120 km/h vector, we get phi is 64.685 degrees. The memo incorrectly uses 25.32 degrees. The memo's angle of 25.32 degrees is actually 90 degrees minus 64.685 degrees. This is the angle from the north axis, which is not what we found from the subtraction, where we found the angle from the east axis. So, the memo's answer is incorrect. Based on our two consistent calculations, the relative velocity of vehicle M with respect to vehicle B is 93.871 kilometers per hour, east 64.685 degrees south. Let's quickly recap what we've learned in this tutorial. We started by calculating the resultant velocity of a ship affected by a current. We saw how to resolve vectors into components, and then used the Pythagorean theorem to find the magnitude and direction. Next, we tackled a projectile motion problem, calculating both the maximum height and the horizontal displacement of a bullet. We saw how to split the initial velocity into vertical and horizontal components to analyze the motion. Finally, we worked through a relative velocity problem, which involves vector subtraction, and we carefully analyzed the solution and the provided memo, identifying and correcting an error. You are now able to calculate resultant velocity, solve projectile motion problems, and determine relative velocity. Excellent work. Thank you for watching. Subscribe for more tutorials from Math Zone African Motives to continue building your skills.